Okay, so good afternoon and welcome back again to our class. So today we will continue what we have done last week, which is the RTL level RTL design or register transfer level design. So last week we have looked at the introduction to the RTL design done already. We also learned how to design the complete digital system, which include the controller and the data path. And we also have looked at RTL operation. And today we will look at the complete RTL design methodology. So last week we have looked at this example. We have designed this data path. We have also designed the controller using or based on the what we call the RTL CS table or control sequence table, and from that we can create the control unit or controller that will sequence the operation of the data path. And we also have looked at the simulation, and today we will look at the full design methodology. And let's look at the design flow, where this is the flow that we need to go through when we want to design a complex digital circuit, including the data path and the control unit. So normally we will start with the algorithmic modeling. And this one actually we will look into detail of designing the algorithm for our application, our system. So it is in chapter 6 actually. And also RTL modeling. This is the translation from the algorithmic model into the RTL model. So RTL model comprises of RTL notation. So for example, here is the RTL modeling. So from RTL modeling, we will create the data path and also the control unit or controller, and also the combination of both data path and control unit. So these three actually we have done last week. We have done already last week. We have the data path, we have the control unit, and we have the integration of data path and the control unit. So actually in the full design flow, when we want to design a digital circuit, we need to start with the specification. So the specification will be modeled using the algorithmic modeling. This one is to translate from the specification to the algorithm, and from the algorithm to RTL modeling before we can get the data path and the controller actually. So from that, we have done also last week. We have done the logic synthesis, where we use the quarters to synthesize our design. Design verification is the simulation. We have done also physical design and implementation. This one we not doing here in the course because we not access to the hardware, right? So if you want to design or want to implement our design in the hardware, then we need to do this, the physical design and implementation. So today we will still look at this part, from the data path designing the control unit, DU into CU/DU integration, logic synthesis, and verification. So this number 3, 4, 5. Number 1 and 2 we will look in detail in the next chapter, chapter 6. So now let's look at the second example, which is example 5.2, where what we want to do is we are required to design a digital system that implement the function of f equal to x plus y by using a data path functional block diagram given in this figure 5.10. The circuit will only perform the operation when the start signal is asserted. The ALU operation are controlled by the OP signal. Here is the OP signal, where if OP equal to 0, F here is equal to A, means that the output here is equal to A, while if OP equal to 1, F here is equal to A plus B. Right, so this is the ALU operation. So what we want to do is to create a circuit that can do this function using this available data path. Means that the data path is provided already. So so what we want to do is we will have a circuit. If we represent our data path as a box like this, and we have the only one input here, which is 4-bit, and the name is data in. Here, data in, and we have the output. Data out, and we have another input. The name is start, right? And also we have the clock, and we have the reset signal. That's it. And this function or this block will implement f equal to x plus y, a simple arithmetic operation. And the data path is given already, so we can model this or describe this in Verilog, yeah, using Verilog. And we need to generate the control signal here at the right time, such that we can get this at the output here, data out. So how to do is to design the controller, yeah, to synchronize the circuit, the signal here, the control signal here, the LD1, LD2, the SEL, and also the OP and the EN at the right time, such that we can get the right output. Okay, so let's do that. So we need to start with designing the data path in Verilog, so we can have the quarters. Okay, we need to create a new project such that we can have that. Okay, so we need this. Okay, so let's use this easier. I hope you can see the screen. So we create a new project. Name it example 5.2. The data path of example 5.2. And use this for the project name. No file to be added. And I select the hardware. Okay, so now let's do this together to describe this in Verilog. So here we have the block diagram, and we have the register here, register number 1 and register number 2, and we have multiplexer here, we have the ALU here, and we have the 3-state buffer here. So this is our module name. We have the clock as the input, reset. We have LD1. We have LD2. We have SEL. We have OP. We have EN. and we have data in, we have data out. Okay, anything else? No. So input is look at the 1 bit. So this clock LD1, LD2, SEL until EN all are 1 bit. So we can have that. And another input is the 4-bit one, data in. Data in. And we have one output, data out. Okay, and we have this Rec1, Rec2. So using Rec data type for these two signal here and here, and the size is still 4-bit. Rec1, Rec2. Okay, so it should be done for the declaration, and we want to create the register, and this part we have the multiplexer in front, right? So we can combine these two together. So this, let's name it as register number 1, where we use the always block, and this is positive H block, and positive reset also. If reset, and remember, when we describe the sequential circuit, we need to use the non-blocking assignment. And if reset equal to 1, so the output here should be equal to 0. So Rec 1 non-blocking assignment equal to 0. Else means that if not reset, else if not reset, we look at the load signal. So if LD1, if LD1 equal to 1, now the input to this register will depend on the output of this multiplexer. So to create this multiplexer, we can use if SEL, if SEL equal to 1, so Rec 1 should be equal to 1, Rec 1 should be equal to data in, else Rec 1 should be, else means that if SEL equal to 0, here, the output here, Rec 1 should be equal to this line, which is data out. Data out. So that will be this one. yeah, and this one, the multiplexer and the register. Now we want to have register number 2, which is this one, and again we can use this syntax clock reset, same thing, and if reset now reg2 should be equal to 0, else if ld2 here, if ld2 equal to 1, so we have reg2 should be equal to data out. Done for register number 2. Now we want to create the ALU here. So we can use the behavioral modeling to model this, and the output here will depend on OP. So we have OP. We also have this, the input to the ALU, reg1, reg2. And we can use if else, if OP equal to 1 or equal to 0, either one. So if we use equal to 1 first, so f should be equal to a plus b. So where is f? F is here, right? So we have f here, right? So this f is a variable in our case, and we need to declare as a variable such that we can assign a value to this. So if OP equal to 1, so f should be equal to reg1 plus reg2, right? Adder. So use plus means that we infer the adder in our design, right? Means that we use the adder in the library. Else f should be equal to a. So what is a? A is reg1, right? So this will be the ALU, and we need to define here also the 3-state buffer. You can use if else also, and you also can use data flow modeling. So if we use the data flow modeling, we can use assign keyword, assign here the output data out equal to we can use this enable if enable equal to 1, data out should be equal to f. Else if enable equal to 0, data out should be in high impedance state, because this is a 3-state buffer when en equal to 1, the data here will go to this line. But if en equal to 0, means that this and this is not connected. Not connected means that this line will be in the high impedance state. So high impedance state in digital or in Verilog can be created using Z, right? So in our case it's 4-bit. So this means that if enable equal to 1, the output here is equal to F. But if enable equal to 0, this should be equal to high impedance state, right? Just like we create the multiplexer, a 2-to-1 multiplexer using the data flow modeling. Right, so that is the this three-state buffer. Anything else? No, we have done. So and module. Okay, so this is the code for this data path. Now we want to see whether the code is correct or not. So we need to synthesize this, and before this we need to save. Click save, and okay, let's see. All right, no error, but we have 6 warning, and we need to check what are those warning. And here is the warning. The first one is of course the license, and this one is the 3-state node. So this one is actually okay, means that the quarters will create the 3-state buffer at this nodes, this line, right? So this warning is okay in our case. Right? Any question in designing the data path? It's straightforward. You see here, although you can see that it looks complicated, but when we know how to represent or how to describe this, for example, this one, yeah, the register, and we have the multiplexer here at the input of the register. So how to create this part in Verilog? Right. So this is how. Yeah. Right. Very actually not that complicated. Yeah. But we need to practice, and we need to understand how this thing works. Right. And the second one is the register number 2. Register number 2 is very easy because we don't have any multiplexer in front of it. So we can create that straight away like this. And this ALU is simple also because the OP is only 1 bit. So it can be either OP equal to 1 or OP equal to 0. If OP equal to 1, so this is the output at F. And if OP equal to 0, this is the output at F. And this is how we create the 3-state buffer, this one. Okay, so any question? Boleh saya tengok yang atas tak? Sebab saya punya F dia tak declare. Okay. Nampak? Okay, dah dapat. Okay. Any other question? Okay, good. Here also, yeah, you can create separately. Means that you can create this multiplexer first, and then you can create this register. But if you do that, you need extra variable here. Yeah, the output of this multiplexer. So need to name this variable here, right? If you create separately, can also, yeah, no problem. Uh, and okay, I have a question for you. So my question is that what if in my code here, if I have this, I describe register 2 first, and then after that I describe register 1, or maybe I describe the ALU first here. All right. So my question is, any different if I do that in terms of the circuit that the quarters synthesize to? Any different? Maybe, so uh, all right. So the answer is yes, no different, yeah, because in Verilog, remember when we code in Verilog, it's not like what we code in computer programming. All right, Verilog is the program, the language to describe the hardware. So hardware means that we describe the structure of the hardware. So it's not run in sequence, means that it need to run this first and then this. If we write like this, it will run simultaneously actually, because we describe this part and here we describe this part. Okay, when the Verilog compiler see this thing, it will read simultaneously. Yeah, it will create this circuit. So doesn't matter whether you want to have ALU first or 3-state buffer first, it will always create the same circuit. All right, because we describe the structure, right? Not how the computer execute the computer programming language, that different. For example, when you code in C programming, for example, right? So the computer will read the code line by line and execute line by line in sequence. So if the sequence is different, so the output will be different, right? That different with this. Yeah, this is a hardware description language where we describe the structure of the hardware. So the Verilog compiler will look at our code and try to create the netlist, the connection, right? So if we describe this, it will create the register for us, one register, and we have this, it will create another register and it will do the connection. So this here, we can see that we describe all the connection. So doesn't matter when you place this before or after, the connection will be still the same, right? So doesn't matter, yeah. Now from that we have this already, so we can check whether it is correct or not actually, where we need to create the test band. But in our case, because the design is very very simple, so we can go forward to create uh, our controller. All right, and we combine this data path to the controller, and after that we try to create the test band and then see the result. And if anything, for example, our result is not correct, we can go back and check our code, yeah, one by one. Should be no problem. So now let's create the controller or the control unit for our this application. So to do that, we need to look back at the specification. So first is that this, and also we have this. Yeah, this start signal is actually the signal that uh, that is used uh, to start the operation of this circuit. So it should be connected to the controller, or should be the input of the controller. So if we create the ASM chart for that operation, so it should look like this, where at the state S0, or the first state, yeah, when we power on our circuit, it will be in the state S0, where there is no operation, and this is always be here whenever the start signal is equal to 0, right? So if no start, it will be in state S0. When start equal to 1, now we start the operation where we will load the value of x into rack1. So x can be any value, right? Because this is variable, right? So x and y can be any value. So, and of course, because our circuit, we have only one input to the circuit. We don't have two input. If we have two input, we can have x in here, y in here, and we can add and we can get the result very easily. But now, because in our circuit, we only have one input here, and that input need to go to rack 1 first before we can add. So what we need to do is, yeah, because we need to add two numbers, and that numbers need to go to our circuit, go to this processing part here, using or through this path only, right? So we need to have x in rack 1 and then send that x to rack 2 before we can load y into rack 1, and then we add, and the result can be saved in either rack 1 or rack 2. So that is depend on what we want to do based on our control sequence or the controller later on. So in this case, so here, first step is to load x into rack 1, right? Load x into rack 1, and we need to keep x in rack 2. So this is how, where we move the content of rack 1, which is x, go to rack 2. Now our x is here in rack 2. Now we need to load y into rack 1. So this is how we load y into rack 1 in S3, and the next clock cycle, we add rack 1 and rack 2, and we store back the result in rack 1. Store the result in rack 1, or you can keep the result in rack 2. Doesn't matter, all right? So it's depend. So in this case, we store the result in rack 1. So this is the ASM that will do this using this data path. So now we have the ASM already. So from that ASM, we can create the CS table or control sequence table. So in this case, for S0, no operation, so no signal are activated. So this can be all 0, right, or all 1. We don't want to do anything or don't care here. So normally we put all 0 here. And when we have start, we go to S1, and this is the, yes, this is the RTL notation, right? So S1, what we want to do is we want to transfer X into rack 1. So what, or how to do that? So we need to activate the correct signal. So how to activate the correct signal? So now we need to imagine that this is our X, and we want this X to go to this REG1. So how to do that? Of course, this multiplexer, we need to select yeah, SEL1 need to set to 1 such that this X will be available here. And to load the data X here into rack 1 here, of course we need to activate this LD1. So that's why in S1 the signal that need to be activated must be SEL1 and LD1, right? So in this case, LD1 equal to 1, SEL1 equal to 1, others we set to 0. And S2, what we want to do is we want to transfer the content of rack 1 into rack 2. So to do that, we need to transfer the data here, go through this through this ALU, go here through this bus, and go to rack 2. So what we need to do is we need to set OP to 0 such that we can get the data from here to here. See, if OP equal to 0, F equal to A. And we need to enable this such that the data can pass to the bus. And to get the data or to load the data into our rack 2, we need to set LD2 equal to 1 in this case. So that is why for S2, the signal OP must be 0. This is a must. EN must be 1. LD2 must be 1. So OP must be 0. EN must be 1. And LD2 must be 1. Now S3, we want to load a new data into rack 1, which is Y, right? Again, to load data into rack 1, so here must be activated and LD1 must be activated. So again, here SEL1 equal to 1, LD1 equal to 1, LD1, SEL1 equal to 1. Now we can load a new data into rack 1. And the last one is to add and save the value in rack 1. So how to add? Of course, the data must be available here. All right, always available here, should be no problem. So OP, now to add A plus B here, so OP should be equal to 1. And to get the data, go to this bus. So EN should be equal to 1. And we want to save in rack 1. So LD1 must be equal to 1 and SEL must be equal to 0. Right? SEL, the name is SEL, yeah, bukan SEL, not SEL1. Can we change this to SEL, SEL, and then SEL. Okay. Right. So to do this, LD1 must be 1, SEL must be 0, OP must be 1, EN must be 1. LD1, 1, SEL must be 0, this OP 1, EN 1. So if we have this, then we can create our finite state machine or the controller. So in our case, we have how many states? We have 5 states. 1, 2, 3, 4, 5. 5 states. So how many flip-flops that we need? Of course, we need 3 flip-flops or 3 bits in our case. So this should be our FBD of the controller. We have the start here, which is here. Yeah, the start is here, and we have clock, we have reset, and we have this. Okay, so this is a typical Moore state machine, right? And we have the CV equal is 5-bit here. Now let's create the Verilog code for this. So let's do this together, and okay, we need this, and let's have a new one. Controller is our name. We don't have any file, and I set to the device that I always use. Okay, create a new one, module, and this is our name. We have clock, we have set, we have start signal, clock reset start here, and we have all the CV, and the CV is this LD1, LD2. So LD1, LD2, what else? SEL, we have OP, and we have EN. Input, we have all are here, 1 bit, and we have output, and should be in direct data type also, because we will describe using behavioral modeling. Okay, all are 1 bit. And remember, now we want to create a finite state machine, and we need to have our state name, where we describe using a parameter, and the size must be 3-bit, and we have f0 equal to 1, equal to 0, s1 equal to 1, s2 equal to 2, s3 equal to 3, s4 equal to 4. Right, so that will be our state. Now we want to create this, the state register. Right, so as always, we use the always block, and this is a negative h, and I have explained already why we use negative h here in the controller, and we use positive h in the data path. So if reset again, our output here, we haven't described this signal, right? So in our case, we use Y, right? In the example, next state and state and next state. So either one you can use either one. So let's for example, in this case, we name this as the state, and this is next state, and this is state, right? So we need to have that using a rect data type. Next state and state. Okay, next state and state. And if reset now equal to 1, so state should be equal to S0, right? State here should be equal to S0 or equal to 0. Else, state should be equal to next state. So that will be our state register, very straightforward. And now we want to describe this next state and the output. So we can name it as next state. Objects. All right. Of course, we need to use the always block. And the input, we have S, start. We'll also have this, which is the state. And we can use case state. Right, at state at 0. Yeah, state at 0. So the output here, CV. So we have CV. We need to create this CV, or you can have this begin LD1 equal to this this, yeah, right, one by one, or you can use the CV equal to how many bits? 5 bit, so 5. And we can use this, all are 0 in state 0, right? But before that, we need to define what is CV, right? So in this case, we need to have another one, right? The size is 4 to 0, and this is CV. Okay, and here we can assign where CV is 0, no, LD1 is actually CV4. LD2 is actually CV3, and so on. So we have LD2. We have what else? We can just copy and paste. We have SEL. We have OP. We have EN. So this should be number 2, should be number 1, and this should be number 0. Right? So if we have this, then we can use CV here. So in this case, if S0, so we have that, and we need to test the start signal. Yeah, we have the start signal. So we need to test here. So we can use if start equal to 1. Next state should be equal to S1. Yeah, next state should be equal to 1. If start equal to 1, so next state should be equal to S1. Else, next state should be equal to S0, means that we remain here. Okay, so that will be for S0, right? Same as this one. And we have S1 begin. So S1 is easy. Now our S1 is not depending on any input anymore, right? So no need to test. And we have the output here should be equal to 1 0 1 0 0 for CV. So CV should be equal to 1 0 1 0 0. Straightforward. You can have N here, and we can copy and paste for the others: S1, S2, S3, S4, and S2. S2 is here. This is S2 0 1 0 1 0 0 1. S3. We forget to have this. So after that, next state should be equal to S2, right? Here also the same. Next state should be equal to 3. S4 should be equal to S0. When we are in S4, go back to S0. Okay, S2 is done. 0 1 0 0 1. S3 1 0 1 0 0. S4 1 0 0 1 1. Okay, all here we have already. So and because we have 3-bit for states, so and we describe only how many state here: 1 2 3 4 5. So we need to have default. This is a must. We can copy here. And let's this be all 0, or you can have don't care. Next state, let's be always as 0. Okay, should be done. So this is n case, and should be done. Right. So can save, and we can start to synthesize our design. And we have again, we have 7 error, and we need to check that error, and this is a good thing. Object LD1 on left hand side of assignment must have net data type. Okay, because LD1, LD1, oh, we have, yeah, because we use assign. No need to use right data type. In this case, we use assign keyword, so we cannot use rect data type to represent this. And anything else? I think that's it. Okay, now we don't have any error except this warning, and this is okay. So this will represent our controller. And before we proceed, any question? Yeah, any question? Okay, so if no question, we will proceed to the integration of this controller and the data path. But remember, when we want to simulate our design, we want to see the state, right? And also in our data path, we want to see also the content of register that we have. So to do that, we need to create a wire, the output that is connected to this, to see the state, right? And because in our design, we don't have any output that connected to the state, so in the simulation we cannot see what is the state value. So to do that, we need to have extra wire that is connected to here, and here, right? 3-bit also, and name it as state. So we need to have extra output, name it state, and here that state is now output, not the rect anymore. So instead of having this state, the state here, we need to create another output called state, and the size is 3-bit. Here, then now we can see the state already. So this is for simulation, right? This is for simulation purpose, and let's synthesize again. Oh, what happened? State is, oh yeah, this is must be rect also. Okay. Done. So also for our data path, so let's go back to data path. Where is our data path? Here. We want to see the content of register here, the content of art register 1, register 2 here. So to do that, we need to have a wire that is tapped, that we tap to this line, and we have that wire to connect it to the output. So at the output part, we can have rec 1 and rec 2, so that we can see. So this rec 2 and rec 1 is now not the rec here anymore, but we need to have another one, which is output. Like this, and it should be in rec data type like this. Now this one is for simulation. Okay, we can save and try to do this, and this is okay. Right, so we have all of the design already. Now we need to combine both, so we need to create a new project. Let's have a new folder. Okay, name this as this. Next, and now we need to add the file. So one is this one, add. Another one is the controller, add. Okay, we have already, yeah. Oh, not yet. So you need to create the Verilog. Module name, this is our name, and of course we have the clock, we have the reset, we have the start, we have the data in, we have the data out, we have the rec 1, we have rec 2, right? So this is something like, we go back to our design here, means that we have a extra output here. This is of course 4-bit. We have rec 1, we have rec 2, and we also have state, which is 3-bit. This one is 4, and we have state. Right? So this is the case. We have state and input. We have these 3 are 1-bit, and we have the 4-bit, which is data in. We have output, which is 4-bit, and we have data out. We have rec 1, we have rec 2, and we also have the state, remember, and this one is 3-bit. Okay, that's it. And now we want to instantiate our previous design. So whereas our previous design, we have two. The first one is this, the data path, and we want this to be here. And let's name this as DU, data path unit. And we want all this to be connected or to be mapped into the new design. And we have the second one, which is the the controller here. And we want this to be here. And let's name this as CU. And of course, we need all of the port here to be here. Okay, everything is done here. Should be and module here. Done. This is the integration of the data path and the controller. And we save the design, and of course we need to save in our folder. Save. And let's see anything. It's not declared as port. Okay, we've missed C, right? So that's it. Okay, we have a warning, and let's see that warning. This is not good. Implicit net for LD1, so means that something is wrong here. Yes, we don't have this declared as in our design. So actually we need to have wire, right? The internal wire between the connection between this LD1 to this LD1. So we need to have LD1, LD2, SEL, OP, EN. 1, 2, 3, 4, 5 bit. Okay. And again, right now we have this 6 warning, and of course the 6 warning is the previous one, which is the 3-state buffer, which is okay. Right, now we have this, and we need to create the test bed. So let's have the test bed. Need to have a new Verilog code for this. So this, you need to have the time scale as usual. Use 1 nanosecond time scale and 1 nanosecond precision. And our module name in this case is, we use this name, EX52, and let's name it TB, which refer to the attachment. And we have this. We can use this, right? The fastest way is to use the same name like this, so that we can just change this to this. Okay, and then we instantiate the our module, which is this one. So the name must be this. And now we need to map the port. So we use the position, which is easy, where we can copy here, put here, should be done. And we can create the simulation in text, where you can use the monitor syntax. And I have example already before this, but in this case, let's say we don't want to do that, so we can skip that, where we can look at the look or see our simulation output in the waveform. But before that, we need to create the clock, where our clock is 20 nanosecond period. Yeah, the period is 20 nanosecond, so we can have something like this, where the clock is toggle every 10 nanosecond. Right, so you can have 20 or 5, depend on your specification. Yeah, so in this case we have 10, and for the simulation, I will use the one that I have here, right, where at time 0 clock start at 0, and we have reset here equal to 1, data in equal to 0, and start equal to 0, and at 30 nanosecond reset equal to 0, at another 20 nanosecond means that the time is 50 nanosecond. So start equal to 1 means that we start the operation, and 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 we see what is the what happened. Yeah, so data in is equal to 2 after we start, and after that data in equal to 5, and after that we have a new start, and the data is different, 4 and 6. Yeah, means that here x equal to 2, y equal to 5. Yeah, because we put 2 first, means that this is x, and after that we have 5, means that this is y. Okay, so we have end module here to mark our end of the line of our attachment, and then we save our attachment. Save our attachment here, save, and we need to check whether we have any syntax error or not. Looks like we don't have any syntax error, so it should be okay. Oh, we have one where we don't have the name for this instantiation, so we should have a name. Give it DUT, design and the test. Okay, now it should be okay, and we try to simulate. We need to have this setting. Remember, need to select our simulation tools, and of course this one is our Verilog netlist, and we want to compile the attachment. So here we need to add the attachment file, and this is the file to add. Okay, and now we can simulate design and wait for the output. Okay, so we have the output here. Here And let's change to unsigned decimal so that we can see the result. So let's see, here is the state here, and this is rack 1, this is rack 2, this is data in, this is start. Yeah, so we can see that when we start equal to 1, now the operation is start automatically here from change from state 0 to 1, 2, 3, 4 and go back to 0 again. And when you have a new start, it will be 1, 2, 3, 4 again until 0. And if you have a new start, you will do again, and it will be always 0 when you don't have any new start. So at state 1, now because we have a equal to 2, not a, sorry, data in equal to 2, means that, and we want to load, right, at state 1, we load data in into rack 1. So we can see that our rack 1 we have here equal to 2 already at state 1. And state 2, we load a new value, right? So let's compare these to this. So we need this. Okay. Right. So at state 2, we move or transfer the content of rack 1 to rack 2. So at state 2, so we have 2 here, we transfer to the next register R2. We can see that 2 here go to 2 at state 2. At state 3, we have a new input to rack 1, and our new input is 5. So we can see that in rack 1 we have 5 here. And state S4, we add the value x plus y, or the content of rack 1 plus the content of rack 2, and we save the result in rack 1. So we expect that the result will be in rack 1 at state 4. So this is state 4. So this is rack 1. So 2 plus 5 is 7. All right, so we have the correct value, 7 here. So this is our x, this is our y. 2 plus 5, we have 7. And if we have the next one, yeah, and the data is changed from 2, 5 to 4, 6. That means that our and the next cycle is 4, 6, x equal to 4, y equal to 6. And look at the result for 6 at state number 4. 4 plus 6, we have 10. So this is correct. All right. And look at this. This is 4 plus 3, and we have 5 at state number 4. We have correct also. Means that our design is, yeah, most likely correct. Yeah, most likely correct. So to make sure that it is always correct, so you need to have many tests. So according to this, we have 3 tests and all are correct. So this is a good indication that our design is most likely correct. All right. So any questions? So we are at 3:35 now. So we will have 5 minutes breaks and come back, look at the exercise. So we actually finished this chapter already. So we have exercise, and we have two exercises. This is the first one, and this is the second one. And we try to do this exercise after the break.